applying similar triangles. This is word problems. And just like last chapter, if the equation, it won't be equation this time. If the diagram is given, you'll probably find it pretty straightforward. You'll probably be like, it doesn't matter that it's a word problem if they're going to give me the diagram. And just like last chapter, if they don't give the diagram, then we got some thunking to do, all right? But I don't think the thunking is that as bad this chapter as last chapter. But we'll see. You decide, all right? When we have to draw the picture yourself. So anyways, learning goal. I'll be able to solve problems using similar triangles in real situations. And this time, when I say in real situations, I kind of mean it. These will be like real situations. And you'll be surprised what you can do with this if you really think about the application of this. So similar triangles can be used to determine lengths that cannot be measured directly. That is, similar triangles can find the distance between two faraway galaxies. You might have to ask yourself, how in the world are they getting those distances when they say, oh, this galaxy is this many million light years away? Like, how are you doing that? Right here, when I finish here today, you can go work at NASA. Oh, you already have that. Yeah. Hey, you can't do everything at NASA, but you can work in one of the departments where they're just measuring angles between stuff and seeing how far away it is. We'll do it on Earth, but I hope you'll see how it can be applied outside of the Earth. Anyways, steps to solving similar triangles. Draw a well-labeled diagram. Well, hopefully, most of the time we have the diagram. So this is for ones that don't have the diagram. Write a let statement. Prove they're similar. Okay, we did that. Let me just put a check mark there. We've been doing that. Prove they're similar. Set up the ratios of corresponding sides. Yes, we've been doing that too. And then find the value of the unknown by solving the purport. Did yours say purport? Oh, mine just got cut off. Yours does say it. Proportion, yes? And then write a therefore statement. A lot of these steps are very familiar with, if you've been keeping up with my lessons or with the homework. Okay. Jump right in. We jump right in with both feet. We're already on slide 3. Here's a preview of the whole lesson. One with a diagram. Another one with a diagram. No diagram. Okay? So if you are peeking at the assignment, for the last one, you want to come back and see me build a diagram. Okay? Anyways. A new bridge is going to be built across a river. There's the river. There's the bridge. A to B is this bridge they're going to build. The question is, how wide is the river? Now, right off the bat, if you really think about this, measuring distance across a river is no joke. Like, I had to measure the distance across my pool to get a new cover. It wasn't that bad. Yes? But it was a little bit troublesome to get that tape measure to go all the way across and try to measure it around. Even that wide, it's like a little bit of a logistical issue. Let's imagine this river's like really wide. And someone said to you, okay, go measure how wide the river is. You're like, what am I going to do, swim across? Drag a string across? Yeah, those could work. You don't have to. Here's what you could do. Yes? You could start at some spot A along the river and walk. It doesn't actually matter how far you walk. Okay? So it doesn't have to be 50 meters. But walk 50 meters downstream like this and mark a spot. Put a pole in the ground. Thunk. No water yet. Yes? I haven't walked across the river yet. Then walk back again, whatever distance you want. This diagram chose 9. Here's the important part. Then walk straight right angle away from the river until you can see your post that you put in the ground. So there's a post right here you've put in the ground. And the other side of the river that's perpendicularly across. You're like, how do you get perpendicularly across? No problem. There's a tree over there, and you just lined up straight across from the tree originally. All very straightforward, and used all the time by surveyors. Then they bring this to you and they say, this is what I did. I did 50 meters, and then I did 9 meters, and when I went 13 meters over and I looked down, ever seen them use one of those little, they're on the side of the road, they got a little tripod and they're looking through a little tiny pair of binoculars. They look straight there, over top of my pole, I could see the tree that was on the opposite side of the river. They were all lined up, and they come to you and say, they tell me we can get the distance across. And you're like, well, okay, first question. did you look straight across the river at a right angle? He says, yes, I used my device. It was straight across. They have little devices that can make sure it's right angle. Just basically a protractor. Say, okay, did you walk, when you went 13 meters, did you go exactly at a right angle? Yes, I did. You're like, then I can estimate it for you. I can do this for you. Step 1, prove the two triangles are similar. Yes? Let me draw the line. That's us. That's us doing two things here at once. Prove it's similar. Ooh, do I need all that space for similar? No. I'm going to save some space here. I think that much space will be enough for me to prove it's similar. I say angle BAC equals angle EDC. They're both 90 degrees. What other angle can I do? Yeah, the opposite ones. You got that one yesterday, right? Opposites. Look for those opposites because they're the easiest ones to find. And I'm going to start labeling them like this. I'm going to put an arc and say, hey, there's an arc. Yeah, right there. Those got to be equal because they're opposite. Not arc. I know it's a river. Yeah, and you're thinking Noah's Ark. No. Ark, A-R-C, not Noah's Ark. Although Noah, when he built his ark, had to do a lot of curved spots on his boat, so he was doing arcs on his ark, but okay. No. Completely unrelated. Just another one of those English language oopses. Like there, and there. Come on. Yeah, I wanted to be there when they did that. I wish I had been there. They're like, oh, let's call that there too. I'm like, no, don't do that. Why would you do that? Ignorant thing to do. Anyways, where was I? Sorry, Alex, I got distracted there. Angle ACB equals angle along the river to C, so D, C, E, and she says they're opposite. Now, folks, I'm overdoing 3 angles. It never had to be 3 angles. That was just me teaching. Stop that. 2 angles is enough. Can anyone tell me in their own words why 2 angles is enough to prove similarity? Yeah, once 2 angles are the same, the third angle has to be the same. So when you see it in books, you'll see it as angle similarity. They just go, once you got 2, you're done. The third one's got to be the same. So therefore, triangle, beep, 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 beep. I'm going to do ABC. Oh, careful. Do the squiggle nice. Squiggle, triangle. Okay, I went along the river and then across. So I went D. Yes, is it there? Over to E. Back to C. That's a little awkward getting those letters in the right order. You got to do your own thing there. I went A to B, so I went straight across the river. So then from the river to the other side, and then so over here I went from the river out. That once you got it started, the rest of it falls into place. By AA similarity. I don't think I wrote it like that just yet, but I want to put that on there. That's the formal way of writing that, is you say by angle similarity. I got 2. All 3 must be the same. I don't know. Your brain maybe is different than mine. That's the hard part to me, staying organized through there. The ratios, hey, that's easy to me. Big over small equals big over small. So big, known, AC over the small version of AC, which is CD, equals unknown. Ooh, label the unknown. W. Let W be the width of the river. If you're not blown away by what's about to happen here, maybe you haven't really thought out what we're about to achieve here. We are not going to cross the river, and we're going to measure its distance across. Will it be perfectly accurate? It'll be as accurate as your 90 is, and as your sight line is, and as your post is, and these 50 and these 9s and 13s. As accurate as that is, that's how accurate you can be. You can do this with 2 stars. If you take, we're in the solar system, and you find the angle when at spring, March 21st, and then you wait until the Earth goes all the way around the sun to the other side, till September 21st, measure the angle to a faraway star, it'll have changed slightly. If you've got an accurate enough instrument, you can really narrow down how far away and what separation there are between galaxies and stars and so on. Really straightforward. And you've got almost all you need right here to go ahead and start doing those things. Oh, and some awesome, and hundreds of thousands of dollars of telescopes and equipment, of course. Yes. Oh, anyways, well, where was I? AC over CD equals, I want to write AB, but I really want to write W. Yeah, I really want to write W over the vertical line, which is the DE. Fill in what you know. AC, and you know what? I got to tell you, most of my grade 12s don't even write that anymore. They just jump to here. They go, listen. And maybe if you've been a little confused about this, maybe the fast version of it, you go, I totally get that. Watch. 50 over 9 equals W over 13. Yes, 50 over 9 equals W over 13. Done quickly, it's like, yeah, of course it does. As long as they're similar, those ratios have to be the same. Now what, friends? Math. Yes, we continue with math. A specific math trick for this one? Algebra. Yeah, it's absolutely called algebra. Cross multiply. So I go with the variable first, me. Nice look. 9W equals 50 times 13, because it just makes me feel better to put that variable on that side. And then I personally solve. You don't have to. You can multiply that and solve. But I guess I only want to go to my calculator once. That's why I do that. 50 times 13, and then divide that thing by 9. It looks like a decimal to me. Well, that's a good question. I've been preaching about fractions. But my question here is, do you think we want the width of the river in fractions or in decimals? It's probably decimal, but I'm not trying to decide for you. I'm trying to mention that usually once we jump into a real world application like this, the decimals are fine. 72.2 meters. Well, that depends. If Apple calls you and wants you to get these distances, you might want to keep it as 72 and 2/9. Yeah, absolutely. If Google calls you to help with their GPS thing, do you think 1 decimal place meters to your house is, yeah, that's probably pretty good for your little Google Maps thing, right? Nobody's checking, nobody's driving home and calling up Google and go, it was 0.1 meters farther to my house. I don't know what you were thinking. Like, we don't really care as long as it's really close, right? So that's starting to add to your wisdom on all this, to going, when decimals, when fractions? Well, you need some perspective on that. So why are we so mean about fractions? Because we want you to be ready. So you can do both. We want you bilingual. We want you to speak fraction and speak decimal. Oh, therefore, the width of the river is 72.2 meters.
Can we also do this with Pythagorean theorem and find the multiplier?
Pythagorean theorem and find the multiplier. Let me do 2 parts. Find the multiplier, yes, you could go 50 divided by 9. Get that multiplier, multiply it by 13. That's doing what this does. What my version of it is just a little more powerful if those numbers are decimals and so on, and you don't have to think it through as much. Pythagorean theorem will get you this diagonal side, which is not what the question asked. But if it did, yes, Pythagorean theorem could get us there. Okay. In the right-angled situation.
Does this whole thing not work if it's not ready?
No, it would work. The problem would be,
You'd be getting an angled distance.
yeah, the problem would be the person would have to walk, and it does happen where you go, I couldn't walk at a 90 because there was rocks in the way. I had to walk at a whatever angle, and then you'd have to change this angle over here. So that all can work fine, actually, when you actually went to do surveying. But in this particular case, did that thing disappear when I walked away? We figured out, see what's happening? Can you see on the board there? It's sensing something. So the calibration's off there. Huh? Oh, random square there at the bottom, is there? No, I got to stop it and calibrate because it's really freaking out now. Ooh, I might have to do this with mouse. Okay. Mrs. Todd, oh, this is a good one. This is true story here coming up. My dad, when he retired, became what's called a tree marker. Get this. He'd go to a forest that somebody owned, maybe someone's got like a 50-acre forest. And he'd go in, because he's a licensed tree marker, and he'd go through with his paint, his can of paint, and he'd mark a bunch of trees. A bunch of trees that actually make that forest healthier if we knock them down. Like if there's two big maple trees growing side by side, this is not efficient. Yes, they're both taking up the sunlight and the nutrients. Cutting one down will let the other one grow more. Meanwhile, the person who owns the forest gets a bunch of money for all this wood because wood is very valuable. Okay? My dad can walk up, no lie, he's practiced a zillion times, he can walk up however high a tree you want. He just walks over and looks at it, gets at a certain angle, and he marks a spot in the ground, and he goes right there. And when they cut the tree down, it's within feet, the top of the tree. So he can do what we're doing here due to experience in his head. Now, I know how he's doing it. You can ask me at the end. I know what angle he's using. It's a very clever angle to use in all this. But you can do this at any angle. Mrs. Todd is standing beside the Leaning Tower of Pisa. No, it's not the Leaning Tower of Pisa. I think she always wants to go to France. So at some point, we're going to have to go to France. But she just did it at a lighthouse at Pordover. Okay? She measures the length of her shadow and the length of the shadow cast by the lighthouse. Okay? Mrs. Todd is 1.6 meters tall. That's a key point in all that, is that Mrs. Todd is 1.6 meters tall. Somebody goes, oh, we actually would probably, sometimes we might want her eye height, and this one, like, no, we want her full height. Her full height is 1.6 meters. And it doesn't actually matter. We put her standing there to help you conceptually. It doesn't actually matter that she's standing right beside here. She just goes out and says, what's my shadow length? And if her shadow length's 4.8, it must be later in the evening, right? Your shadow at noon is nothing, but as the day goes on, it gets longer and longer. So she's got a fairly long shadow here. But notice what she's created here. She's created similar triangles. Can I convince you they're similar? She's standing straight up because she's got incredible posture, folks. The lighthouse is standing straight up because they build them to stand straight up, usually. Yeah? The light beams coming in are hitting the ground at the same angle. Yes? Whether you're going off the lighthouse or off Mrs. Todd, the light beams are hitting at the same angle. So they must be similar triangles. I'll write that in words instead of the fancy language that time. Both Mrs. Todd and the lighthouse are at 90 degrees. The light rays hit the ground at the same angle. And in the case of the diagram, I hope that you really are convinced that's true, because we made in the diagram Mrs. Todd stand right in the line of the shadow, like she's in the perfect spot. Therefore, the two triangles are similar. And again, you can measure the height of light. Imagine if you actually wanted to measure the height of the lighthouse. You'd have to go up to the top of it with the longest string or rope you ever found. Hang it down. Hopefully the breeze is not going. Have someone hang it straight down. Then get your tape measure out and measure and measure and measure and measure.
Isn't there laser pointer guns that like laser point the distance?
There are rangefinders that do those kind of things. And so those will work in many situations nowadays. That's a modern way to do it. They will not work on things like stars and the bottoms of oceans and the tops of mountains. Yes? Whereas this method can work with anything. What's that?
Is that because like the water distorts light?
Yeah, the lasers are a problem, right? Lasers they're relying on light, and so when it hits the ocean, it's going to change its angle, and that throws everything off. Doesn't throw my method off though. But you're right. Modern applications give us some options here. Yeah.
Why would they just like throw a rope off of the lighthouse? Like some guys holding it.
He's so right. There are some lighthouses that you could probably now. If you wanted to have a race though, you and I, you got your rope, and you can even pre-measure your rope. You can mark it off 6 feet, 6 feet, 6 feet. You go walk up the staircase to the lighthouse. I'll go over and measure Mrs. Todd. You won't even be to the first flight. You'll be halfway up going, and I'll be like, I got it. We're done down here. Yeah? And if I'm accurate with my measurements of Mrs. Todd in the shadows, I'll do really good. Will I do as good as you with an exact measuring tape? Maybe not. You might do, like 1% better or something like that. You might. Now, the other answer I considered was, okay, let's say we're doing the same situation, but you're doing the measurement between two stars. You can't go out to the star and drop a rope down to the next star. Yeah? Well, you should go. Definitely go. Get in your spaceship and go.
Mr. Todd, nothing is impossible.
I never said anything you wanted to do was impossible. What I said was, I'll be done in a few seconds. You'll be several light years. My life will be over by the time you get back. Yours won't, because you're traveling at high speed, so you age differently.
Yeah, but wouldn't the rope break because you have like, can you lift the rope on the gravity of the body?
Get ready. Get ready. This part is supposed to blow your mind. And blow your mind in a good way. You're like, oh, this is pretty straightforward, really. I marked the height. Let X be the lighthouse height. I must tell you, my grade 12s, for similar triangles, they don't go through some of the nonsense we do. They just look at this and go, I got it. X over 1.6. That ratio, whatever multiplier it is, to get from X to 1.6 is the same multiplier as 75 to 4.8. And now I'm at the bottom of the White House, and I'm going to order a slice of pizza and a Pepsi and still beat you as you run up the lighthouse. Because all I got left is cross multiply, right? 4.8x. Even if there is an elevator. Even if there was an elevator. As you're waiting for it to get from the top to the bottom, you're right, I might not finish my Pepsi, but I'll get the slice of pizza down by the time you get this figured out.
Who only needs one slice of pizza though?
Is it dress down day? Is that what's causing all this? It's actually day, is it? Well, actually, do you have a friend like that who's like, well, actually, Mr. Todd. Now, I know I selected nice numbers here so that you can look at it and go, well, I could see it was 1/3 to begin with. I didn't need all your fancy math to do this question. I know, but really, it might not be 4.8 and 75. It might be like Mrs. Todd's exactly 1.6. She's probably 1.63, and so this handles any crazy decimals that come along, right? Therefore, the lighthouse is 25 meters tall. I don't know if you're ready for this or not. This question could be done. I'll do it in blue up here. This question could be done within the triangles as well. It works. You could have done 1.6 over 4.8 equals x over 75. That totally works as well. And moving forward, we might switch over to that version of it because it gives the exact same answers. Okay? You're going height over width equals height over width. That proportion's true as well, and has to be, or else math is broken. Okay? All right. Questions there? Okay, this is the one. If you've started to work on the assignment or you're busy trying to come up with questions to distract me, We might want to shut it down for this one because it's a word problem. Now, no diagram, but I'm hoping when we read it, we can draw the diagram, okay? I'll read it once, fast, and then I'll slow it down to try and figure out what the heck is going on. A hiker whose eye level is 2 meters above the ground wants to find the height of a tree. He places a mirror on the ground 20 meters from the base of the tree and finds if he stands at point C, which is 4 meters from B, he can see the reflection on the top of the tree. How tall is the tree? Shh, shh. No. No distracting questions this time. No derailing. Just stick with me as I draw this out, okay? Because it's not that bad if you just take it a piece of time. You try and read the whole question. Yeah, good luck. After all that, I know there's some ground. Will you draw some ground, please? Is it ground? Mr. Todd, the ground's round, not flat. Shut up. It's flat. Here, right here. It's flat right here. Then we need the person. I hope you're better at drawing people than me. Hiker. Little stick figure. And he's 2 meters tall?
No, his eye level is 2 meters tall.
Yes.
So he's like 2.1. Probably.
Then I need a tree. I encourage you to draw your trees like me, not because I'm terrible at drawing trees. It can get confusing if you put a lot of branches on there. So here's my tree. Oops. Straight line tree coming at you. And all I'm going to do is put, there's my tree. You can put all the branches on, but that might mess up your triangles a little bit. So there's tree. I am Groot. Tree, how tall is the tree? Oh, that's how we're trying to find. X, H, whatever you want it to be. Let H be height of Groot. Okay? Well, geez, I hope that's not too tough a diagram so far. Okay? I hope you're like, okay, I can do that. Switch colors. I'm switching colors. Shh. Okay. He places a mirror horizontally on the ground 20 meters from the tree. And find, okay, 20 meters from the tree. So out here somewhere, I don't know exactly where, somewhere over here, mirror. This works, by the way. This is a great way to do it. And most people who do this feel very confident about the situation. They feel great about what's happening. Shh. Okay, random comment time's over. You used them all up. And I need a little tiny bit of physics here. Light rays bounce off of mirrors at the same angle they come in. Did you do that in science? Yeah. Oh, well, I don't need to teach any physics at all. That makes perfect sense to me. A ball would bounce off at the same angle it came in. So do light rays. Light rays act like that as well. That's great news for us because due to light rays, and that the hiker is looking right in and can see the top of the tree in the mirror, those angles have to be the same. The tree is going straight up, and if it's not going straight up, we can account for that. We can account for that if it's not going straight up. Not yet, we can't. The hiker is standing straight up, and do you see I have similar triangles? Yes? I'll just mention that. And since you took physics, I'll throw in one word there. Or you took a little bit of science. It bounces off of the instant angle. Both the hiker the tree are at a 90, and we can deal with it if it's slightly off. If it's not quite at 90, we find a spot that is at 90 and we work off of that. So that's not a big problem. Therefore, the triangles are similar. And I say the rest is getting easier the more times you see it. Large over large. H over, I'm going to do it right in the triangle. H over 2. That height over 2 equals, ooh, I didn't label. How far away is this thing? 20 meters here. And for you future engineers and draftsmen, that's how we do this. Draw these lines on to help us label these. What was the other one? 4? Yep. And again, yes, I've used very nice numbers where you go, oh, it's multiplied by 5. Okay, yeah, that's fine. But if it wasn't nice numbers, you're going to want my proportions. Yes? H over 2 equals 20 over 4. Cross multiply. I don't know why I switched to X there randomly. Therefore, the tree is 10 meters high. Last thing before I wrap up, I want you to know these are the methods that people use all the time to calculate what are called inaccessible distances. Not easy, and if you going up a lighthouse is easy. Climbing to the top of a tree is no joke. Yes, even one of those pine trees that are pretty easy to climb, even though you get a lot of sap in your hands. I grew up in the country when I was a kid and we climbed a lot of trees, but the average tree, getting to the top of it, or even getting a rope to the top of it, and then getting it to hang straight down a tree with all the branches in the way, these are major league problems. But this is pretty easy. And like I say, my dad, okay, to finish my story, my dad uses 45. He's pretty good at estimating 45 in his head. So if he backs away from a tree and knows it's at a 45, he knows it's an isosceles triangle, he knows his distance to the tree is the height of the tree. So he's very clever about it because he has to do it very quickly because he's got to write down, here's how high this tree is going to be, here's how much money you're going to make from it when you cut it down. Yeah? Do you have any questions about any of that?